that's what I have. So I'll post homework 4 solutions later today, so you could look at those. But the purpose of today is doing a review for the exam, looking at the problem, answering questions. So in terms of this first exam, right, material for it, we've had 4 homeworks. There's notes from lecture, there's material in the book. Primarily we're looking at chapters 1 through 3. Double check. Always make sure which some books have, I'm getting the right book in mind. Right? They're probably chapters 1 through 4, right? Just to give a little bit of chapter 4 is the discrete distributions. And we did some of that. Binomial, Poisson primarily. For these, binomial and Poisson. We also looked at geometric, but it's not really described in the book so much. It's good to see another example, but the exam will focus on those, so the probability formulas for those. So the idea is, or the recommend, in terms of like a list of topics that we've done. And at the beginning, we looked at studies and the value of randomization, or in surveys, random selection, getting something that's representative of the population. And we did that in a not too technical way, but when something's described as being a data set or being statistics that are summarizing something about a sample, if you don't know how that sample was arrived at, or it possibly could have been arrived through volunteers or some other selection mechanism that didn't make everything equal, there could be some bias. So every conclusion based on that has to be taken with a little bit of care. We did some describing of data. So once we do a study and get a data set, the main descriptions we had were measures of center, things like X-bar, the median, spread. We look at standard deviation, interquartile range, things like that, the range. Might have looked for outliers and graphs of things, right? Histogram, box plot, things like that, and related things to one versus the other. Here we go. We're just going over some of the things that would be on the exam. Besides that, we looked at some probability rules and kind of things mostly with Venn diagram. Venn diagram, probability rules. For a few things about probability. There was some conditional probability. Making a tree, doing something with Bayes' rule, and inverting a probability from conditioning on one thing to going the other direction. Within this, we looked a little bit at sensitivity, specificity. And mod and things like that. Primarily, I'm going to focus on the sensitivity or specificity. Maybe we'll get a little guidance on those different meanings of those things, right? But kind of once, if you're told what they are and use a number for it, what does it mean? And then binomial distribution as a discrete distribution, and Poisson as another example for the primary things that we've done in this. Right? So if you look back over some the homework, and again, homework 4 solutions will be posted, later today. They're ready. I just want to give people a chance to do a little bit more. And the lecture and the book. It's closed books. You do need to know formulas. There's only a few formulas really that we have that we're using. For the describing things, there's the average, right? Just x1, x2, right, up to xn. Finding the median of a few data points. We had the sample variance, where we would take the x, I'll write it as a sum, of the xi's minus this x bar squared. And take that, and standard deviation is the square root of that thing, which is called final S. Right. So the descriptive, that was most of it, looking at a graph and pulling off some things. Right? If I ask you to describe something, right, you can describe a lot of different things. Range, smallest value, biggest value, where you think the average is, where there's clumps of data, how it piles up, are there any outliers, skewness. Yes?
What is that S squared again? Variance?
S squared, so this is the sample variance. And this would be the sample standard deviation. As a calculation for doing that. Now you might, I could give you a few data points and have you calculate some of these things. I also could give you numbers, and you could provide some interpretation about, where's the average, where's the standard deviation. Maybe compare groups. Yes?
What's the format?
So the format of the test is, so I give, I write out the problem. So this was how it kind of looked last time. Well, that's smaller. But you can kind of see it in the solution. So this was from last year, right? So there's a question, and then there's some space, and you just write on there. And so there's like here's a graph, and there's usually should be enough space to put the answers in there. 4 or 5, maybe 6 problems, I don't know, but 2 or 3 parts each. So say there's 15 little ABC parts. So in an hour, it's about 4 minutes per ABC part, which is doable if you can do, some of them a little faster, then have a little more time to think about what the question means and think about a response. And so you do need to move along through it, but there's not going to be 50 parts. It's going to be more of what I hope is in my past experience, has been a reasonable number. So yeah, like that, and then the second question comes, and there's a little bit of space in there to do those. You need a calculator to finish some of the calculations. You can use whatever calculator you have. Pen or pencil is fine. Don't use a phone during the exam. So do check that you have a calculator. Everybody should have their own $10 or $15 calculator, or a more expensive one is fine. In terms of formulas, right? So the binomial distribution, there's a sample size n and a probability p, and the values that can happen 0, 1, 2, up to n is counting the number of successes. So the probability that x equals one of these values is as n choose x, p to the x, 1 minus p, n minus x. And the average value or expectation is n times p. And the variance is n times p times 1 minus p. And the standard deviation is the square root of x. So it would be fine to, as soon as you get the exam, write down a formula, if you're trying to memorize it, and then there's a couple key things you want to write down. You can remember those. The binomial, n trials times the probability, that's a little intuitive, right, for that one. We've done, kind of tried to motivate that and do a few different calculations along those lines. The other probability formula that kind of finishes out the list of probabilities. If you have a random variable that's Poisson with a certain rate, again, it can take on the integers, but it can possibly go forever. And the chance that you have a certain outcome y is e to the negative lambda, lambda to the y over y factorial. And the expected value of this is lambda and Poisson. It turns out the variance is also lambda. So the standard deviation is the square root of lambda. And that describes the spread pretty well. So that's kind of it for the most of the formulas. I have to do a little reasoning about Venn diagrams and probability, right? So maybe we can write that one down to give you that one. I'll write that on the next page. Well, I'll get it here. Right now. If you had two, yeah, it'll go on the next page. You have a little more space. I'll do this one. I'll just erase it here. Put it on the next page so there's more space. So this probability for like a Venn diagram that had two cases. The probability that you have either one, A or B, can be calculated as the probability of A plus the probability of B minus the intersection. Or this is the probability of both. And here in the middle, that's both. Outside is neither one. And A is the full big circle of A, and B is the full circle of B. So let's look at some questions. But any questions before you want to ask about before we look at one of the sets of the exams? There's 3 sets of questions there. So I said we'd go through one, but then there's time in case you have other questions too. So one of these questions so there's these 4 snowstorms at certain inches, and what's the average, what's the median, which is measurement is sensitive to individual values and why. And then there's the part B where there's a box plot of the data. Describe at least 2 features of the box plot. What are 2 features of the box plot that you can describe? Yeah.
The bold line is the median.
Yeah, the bold line is the median. So you can write on the test paper as you want, right? So you can write there's the median. It looks, this is 40 storms. That's the difference. Before it was just 4 numbers. Bigger things. So I don't know, you can look like it's about 1.5, something like that, kind of eyeball it. But between 0 and 2, maybe closer to 1. Right. So good, that's one thing. Anything else? Yeah.
It's a little bit skewed right.
A little skew to the right, skew to the longer things. If it was tilted on its side, it would, you'd see that tail sticking it up. Right. A little skew to the right. But it's kind of wide open. Right? Say the minimum looks just about 0. Right? Maybe there's 0.1 inches. Right? Something like that. Maximum, good 13, 14 inches. The interquartile range, it looks like 50% of them are somewhere between about 1 and 4 inches. You can see there's 3 outliers. 3 storms are marked as outliers because they're big. Like all those things are fine to say. The numbers there, I don't ask the same thing on every tests, so some things you study from these won't exactly be asked, and but some things from homework might go in there. So, but these are kind of representative of the range of things. So for snowstorms, we had 2 inches, 1 inch, 1 inch, and 8.4. That's what it was. Yep. So we can get the average value, 1 plus 1 plus 2 plus 8.4 over 4. So that's 10, 12.4 over 4, or 3.1 inches on average. Median, if you put them in order, it's going to be about 1.5 inches. 1, 1, 2, 1, 1, 2, 8.4. Kind of between these two would be 1.5 inches. Which one's sensitive to an extreme value? Yeah.
Wait, shouldn't that be over 5? Because there's 5. Or
This is one. It just has 4 values here.
oh, okay.
Right. And this, I'm just taking the midpoint here, about 1.5 inches. Say that's the median. Right? So there's 4 actual storms. They were divided by 4. Which one's sensitive to extremes? Yeah? Yeah, the mean. So this has been 18.4 inches. It would make the mean go up, but it wouldn't change the median because you still have that center there, right? So mean is sensitive. So you could say each data point directly impacts the mean, but only the center affects the median. Or you could say if this had been big, right, it would change the mean, but not the median. If you give a numerical example, just reason a number of ways to explain that. In terms of that standard deviation formula, it would say take 1 minus the average, 3.1, and 1 minus 3.1, and 2 minus 3.1, and 8.4 minus 3.1. And then square those. So the squares get rid of the negatives. So this is 2.1 squared. This is 2.1 squared. This is 1.1 squared. And this one is 5.3 squared. And if you add those up and divide by n minus 1, which is 3 in this case, that's s squared. So the numerical value of this thing, I'll pop over here to I'll come back to that in just a second. So if I go to just, might as well do our studio. So if it had asked for that, we would compute this thing. So let me get this out of here. So we would have had the 2.1 squared plus the 2.1 squared plus the 1.1 squared plus the 5.3 squared, and 38.12, and then we divided by 3, and that's s squared, right? That's the sample variance. And then we get the square root of that thing. So about 3.6, 3.57 as a standard deviation. Yes?
Why was it 3 divided by 3? Because
Because in the formula you divide by n minus 1.
oh, and minus 1.
Yeah. And so in this case it was 4, just small sample, right? 4 storms. But that's the first problem. Any questions about? So yeah, so you show formulas and you show some calculations in the way. You want to not spend a huge amount of time, writing out every possible description. If it asks for 2 and you give 2 that are kind of different and you think are accurate, that's enough. You don't necessarily have to write everything you might think of. If you have time at the end and are going back through it and say, oh, I know one more thing, and can reliably put in one more thing, you can do that. But if it says 2, 2 is fine. So here's an alpine ski racer, has a 70% chance of improving her time when the wind on the mountain has a low velocity, and there's a 25% chance of improving when the wind has a medium or high velocity. The wind has low velocity about 40% of the time. So what's the probability of improving? Would you, based on what it says there, what are you thinking about in terms of approaching the problem? Yeah.
All those block ones.
Like a tree?
Yeah.
Yeah. You said block, but your fingers were doing the
Right,
trees. Oh,
yeah.
that's,
I have no
Yeah.
idea on that.
yeah, that's fine. Right. So, but yeah, a tree type thing. So, you know, when you see one like this, you can circle these different probabilities that you need to have. Right. If that is easy, right? So the wind is low, or you know, medium to high. 40% of the time it's low, so 60% of the time it's medium or high. This skier either improves or does not improve. And right, so there's a 70% chance of improving in this condition, and a 25 in this one. So what's the chance she improves her time? Well, if you multiply these out, 0.4 times 0.7 is 0.28. And then on this lower half, so 0.6 times 0.25, so a quarter of 0.6 is 0.15. And those are the two places where she improves. You add those together. So 0.28 plus 0.15 is 0.43, so 43% of the time. There's 25% here and 70% here, and it's almost an equal split, but a little bit more on the medium-high winds. So 0.43 is between those two. How about, see, are improving your time and the velocity of the wind independent of one another? So why is it not? Yes?
Well, for there to be low wind velocity, there can't be high wind velocity. They can't both happen at the same time. So
Right.
one
So
or the other.
yeah, one or the other happens. Right? But in comparing, does she improve her time versus the velocity? Right? You can't have both of those things happen together. Are those independent things? Is whether she improves independent of whether or not? Is there any difference in the probabilities? Yes.
If the wind's high, she has a lesser chance of improving.
Yeah, right. High wind is less. These conditional probabilities are different, so they can't be independent. Right? If you took the chance of low and improving as a product of those two things, that's 0.28. But if you take 0.4 low times 0.43 improving overall, you don't get back that 0.28. Right? You can't get it. So. But the key thing is the probabilities change depending on the wind. So they're not independent. They're changing the chances. This one is the Bayes type one. She improves her time. What is the probability that they had a low velocity? Writing it in symbols, you know, don't let that, you know, don't rely on that necessarily. You don't have to rely on that to answer the question. So. But here's where it's low and it improves. Here's where it improves overall. So what fraction of the time is she up here, given that she's in one of those two? So what's the probability the wind is low velocity, given that she's improved? Well, there's a 0.28 over the 0.443 is the answer to that one. Which is a little bit higher than 40%, right? Because improving is more associated with the low velocity. On the answer sheet that's there, oops, all that wonderful stuff, great. Get it off of there. I never quite figured out how to do that well to save it. But that's that one. This next one, here's the full tree. This particular question just actually asked about the upper ones. It's a little bit messy, but it's 0.43. The probability that the student improves their time, with the ratio of things about 65%. You draw a tree, you write symbols, you write it in words. Okay. Yes?
Do you want us to convert that into a percentage?
You could leave it just as a decimal. So you could either write this or 65%, either one. They're equivalent in terms of their value. So if I phrase the question in terms of probability or percent, you can keep it as a decimal or change it to a percent. Either one will work out. So the third one on this question, here's a wrist strains and fractures. I think this should be a W. Wrist strains and fractures are common injuries that occur among individuals who go snowboarding. So there's 200 snowboarders recruited for a study. Half were given a wrist wrap and half were given a wrist guard, which is more solid, right? And the rate of injuries, right, were recorded for each group. So what type of study does that seem to be? Doing a survey. So it looks like a comparative experiment, right? You're comparing wrist guards to wrist wraps. How would you use randomization in this study? Yes?
Would you do the one where you like match the people up?
You could match the people up, yeah. So if you had, say, pairs coming by, like you would random flip a coin and give one in the pair a wrist guard and the other one a wrist wrap, right? And then see who gets hurt, or report some strength. You might ask them other things about their comfort or enjoyment and so on as well. But if the people are coming together, maybe they're kind of similar in abilities, similar in styles, going to the same parts of the slopes. Right? And then if you randomize them, flip a coin, one gets the other, one gets that, kind of a fair comparison. Or you could just take people as they come and flip a coin and somebody gets one or the other. Right? Or you could alternate, or at the end you can make it balanced, so you get 100 of each. Right? But that should be a fair comparison, right? What are a couple additional variables you might record? Well, I mentioned, do they like it? Do they? Right? But anything else? Age, right? You could report more characteristics about the snowboarders themselves. Yes?
Determine their sex.
Yes. You can ask them that, male or female, or ask them to report something. Right? You can ask them their experience. So it's kind of wide open. Right? Anything that might reasonably affect their chances of an accident or their style of snowboarding, you could ask about it. You could have somebody down there with a speed camera thing, trying to figure out how fast people are going. Observing them. Do they see like they're doing any stunts? You might even, these days give them a Fitbit or something that clocks their speed or how long they're snowboarding on a given day. So instead of randomizing snowboarders in two groups, consider simply asking a large group of snowboarders if they, that are already there, are you wearing a wrist wrap or your wrist guards? Have you had a wrist strain or fracture? What would be either a limitation or benefit of just asking the people that are out there? Yeah.
Limitations, and you don't really know how many people are going to be in the study, so it could be like really small, and that's not overall great.
Yeah, if you only can do it one day and there was not many people, you might have a small sample size. But if it's a big slope and you're going, big mountain and you're going on the weekends, you could probably still get quite a few. But yeah, sample size could be an issue if you're not putting more control into it. Right? Anything else? Would results from this type of thing be as convincing to you as a randomized study? Why would they be less convincing?
Bias.
Yeah, there's some bias, right? Some people might, maybe they're novices, they wear the more protective gear, maybe they're younger, their parents force them to wear the protective gear, they're a little bit older, more experienced, they don't use as much, right? So whether they get hurt or not could depend on their experience level or their, you know, how aggressive they are, and not really depend on those protective gear, right, as much. But with the randomization, we try to take out most of those other factors and just have the screening comparisons. But it might have a benefit, right? It might be quicker. You know, people are already wearing these things. You don't have to try to get them back at the end of the day. You know, people might leave with them, and so then you have to bring all these things there. But if people already have their gear, possibly you can interview a much broader group faster, right? Than getting people to this randomization business. So both studies, type of data could go together. You might collect a bunch of data from a group that you just talked to on the slopes, but then do another part that's the randomization, and kind of interesting to see how they compare. There are a few questions put together. So an ice fisherman goes fishing 9 days in a row. On each day, there's a 20% chance of catching enough fish for dinner. Both the days are independent. What is probably the ice catches enough fish for dinner on 2 days? So there's ice fishermen. So in this one, there are 9 days. The probability of enough fish being caught was 20%. What's the probability that they catch enough for 2 days? What type of random variable does this look like? Yeah. Yeah. This is the kind of the setup for the binomial, right? Independent days, a certain number of days, a certain probability. So the formula was 9 choose 2. Let's pick 2 of those days. There's success on 2 days, 1 minus that on the other 7 days. 9 choose 2. Calculating 9 choose 2. 9 times 8, take 2 numbers because we're choosing 2, and divide by 2 times 1. So that's 4, that's 36. So 36 times 0.2 squared, and times 0.8 to the 7th is the solution. Let's see, the solution one. As we go down, here was the study. See, some of these answers could be kind of short. This is the one here. This turns out to be 0.302, 30% of the time. This fisherman, the ice fisherman, is going to catch enough fish for dinner on 2 days out of 9 out there. Suppose 200 people go ice fishing, and they each have a 20% chance to catch enough. Right. Suppose they're independent of one another. If you're taking people that are clumped in groups or sharing the same ice house or something like that, then they're probably not independent because the results for one are similar to the results for the other. Right. What's the expected number and standard deviation? So we have N and P. The expected value is 20 times that 40 out of 200 people. The standard deviation is the square root of the variance. The variance is, this is N times P times 1 minus P. So 200 times 0.2 times 0.8. And so the square root of 32, and so it's 5.66. These are actually people catching enough fish, and the standard deviation is the number also relevant to the number of people. So usually we think about the mean plus or minus a couple standard deviations. A couple standard deviations is about 11. So 40 plus or minus 11 is usually the number, the type of, out of 200 people, the number that you're going to get, somewhere in that range. Around 40, but it could go down to 30 to 50, maybe a little bit more than that. What would happen? And so, see here a study of people who catch enough fish for dinner through the ice fishing records. records the number of hours spent fishing. Would the outcome in this study have the same distribution as the one considered in the other ones? Is it a quantitative, is it a binomial again if you ask how many hours you're going fishing? No, it's a quantitative variable. Right? So it's distinguishing the type of thing that you're measuring. Is it a binomial model? Right? So yeah, it would fail being a binomial if they weren't independent. Right? So if you had clusters of people, right? If some people are experts and some are novices, well, maybe the experts have a better chance of catching a fish. Right? So maybe the probabilities aren't the same. So there's a few ways that if you say you're going to go talk to people until you found somebody who caught more than 6 fish, right? And you're not setting a limit on how many people you're talking to, right? Then the sample size is fixed, and it's more like a geometric. I don't plan to ask any geometric formulas, but it's kind of a counter example to the binomial. Okay. So that's the fish one. This one is about hand grip strength. Now, when I asked this last year, we had talked about the normal distribution. So this one was made about the normal distribution. So the solution that's posted is the solution from that last year that said something about normal, but I revised the question, right, to be relevant for what we're doing. Right? So the key thing in this revision is there's kind of a rate out of 1,000 men here that have a very strong right hand grip strength. So in a group of 1,000 men, what are the chances that you find at least 4 with right hand grip strength in excess of 70? So the type, when it says kind of a rate, like 4.2 out of 1,000, that's like a Poisson random variable, right? That's, so 4.2 out of 1,000 is like a Poisson random variable. And it asks, out of 1,000, what's the chance you find at least 4, and then mean standard deviation. So at least 4. There's a probability that you can get 4, 5, 6 on forever. We're not going to calculate that. We're going to calculate the 1 minus the output.
One minus some probabilities between 0 and 3?
Yeah. So those different ones. This is 1 minus the probability that it's less than or equal to 3. And this is the probability, this one is that y is greater than or equal to 4. So, and Poisson probabilities, I might not ask you that many, but to make this a study question, right? So the probability is y is 0, is e to the negative 4.2, because it's a 4.2 rate in here. And then as you, each time you add 1, you get a rate out front, e to the negative 4.2, and you divide by that number. So y is 2, there's a 4.2 squared, e to the negative 4.2 over 2. It's really 2 factorial. 1 factorial is 1, 2 factorial is 2 times 1 is just 2. The next one is 3 factorial, which is 3 times 2 times 1, which is 6, multiplies. So the probability that y equals 3 is 4.2 cubed, e to the negative 4.2 over 3 factorial. And you'd add those up and subtract it from 1. On the website, I made a modified solution for that 5th problem because it's different. Right. So this one is this is posted for this review of the exam. So if these formulas here, calculate them, and it ends up being 0.395. So the probability you get at least 4 is about 60%. For Poisson, the mean and variance are both that 4.2 rate. That's the standard deviation, just the square square root of that number, a little over 2. And this is counting the number of men that have this grip strength out of 1,000. And then they asked, was independence important? Well, it turns out, you know, if we do assume that these men are independent in this, and the grip strength of one doesn't depend on the grip strength of other. It would not be independent if they were in clusters, like you get a group of men at a retirement home versus a group of athletes in college or something else. If you're taking clusters of individuals, then they're probably more similar than randomly selected people. So it would kind of invalidate the chances and probabilities. Right? If you happen to get a group of athletes who are really strong into the sample, then you'd get much more than 4. And so that would probably boost those extreme probabilities. But anyway, so some discussion of that. So those are, that's one exam, right? Of those, this was based on research study, so these numbers, but anyway, that is right, doing those 5 questions would be one exam. Right? The material that's available for study, so under assignments, under the exam one here, right? There's a lot of things, right? So here are the study problems in either Word or PDF format, depending on what you need. We've talked about this first one, but there's a couple other sets of questions that go through things, right? And then the solutions, and here's this modified problem 5. The same thing happened for those 2 review problems that I had from before. They included a normal probability question because I think the semester started on a Wednesday, and so everything was off by a day or 2. So we're almost there, and not behind where it was last year, but it was just a slight change. Right? So it's not on this. We're focusing on these discrete ones. But if you want to see the solution to that modified part of 1 or 2, it is there too. So that's that one. Questions on anything?
Just like how we know when to use what. So like we'd use the diagram and the tree if we were looking at like dependent stuff.
So that's, that's a key thing. How do you know what to use, right? So if it gives you a probability of one event, right? So that so it gives you a probability of some event, and then says, well, if that's true, then something else is happening. However, if that's not true, then the chances are like this. Right? So you're going to have A and then the opposite of A here with 2 probabilities. And then there's the chances of the conditional probabilities. And so if it gives you the chance of some yes or no, high or low, some category, and then the chance of something else conditional on that, among this group, we have this rate, then it's kind of setting up one of these trees. So that's kind of giving you at least 3 probabilities like that. There's usually not a mention of sample size or other measurements and things like that. So those 3 probabilities is enough for that one. Binomial formulas, there's in trials, or in people, or in animals, or just some number in there, and there's some probability of success for each one. And then it's asking for how many out of n. The chance you have 3 happen, 4 happen, something like that out of the total. So it has to give you a sample size and a probability, something about counting the number of successes. With Poisson 1, it's going to give you a rate. You say out of 1,000 people, out of 10,000 people, the rate is 2.5. And it usually those are pretty smaller rates. Most of the examples I think about are 2.5, 3.6, smaller numbers like that. So Poisson, you're looking for a rate. We get some rate. And, this rate is often out of a large number. Now it's possible a number of those problems, the Poisson runs could be done. Well, let's not get confused with that. If it says a rate like that, it's going to really, thinking about Poisson, that'll be the quickest thing. The Venn diagram type stuff, it's going to use one of these things like, you have the probability of this group, the probability of that group, maybe both of them, maybe neither of them, either one, that type of language gets used. So this is the little area in here would be both. You have something like this. This is the probability of neither one would come out here. You have either one, A or B. It's kind of this whole area in there. Sorry, that's a little messy. Now they're so it's going to use that language like this one, but not that one, or something like that to figure it out. If it gives you a set of numbers, it's asking for average, median. The ones that have actual numerical values are a little bit different. Any other? Questions? Any questions from past homework? Do you want to look at any of the questions from a past one, just to kind of talk through identifying what it might be asking about? Let's do one of these and not answer all the questions. So this review one. Oh my gosh, I'm gonna get back to it. Yeah, right. We won't go through and answer everything, but we can at least read the questions and think about how would we know what to do. So if it starts out with a graph like that, it's probably going to be describing a graph. Right? And it gives you a few values in ages and years, mean, median, standard deviation, so it's a descriptive problem. The second one is a survey. So there's like a table of counts. And then it's proportion derived from the table. Whenever you see a table like this, you might add up to get the totals on the side. So it'll be useful probably to have at 11, 210 there, and then 180 here. Wait, that's 11, 220. And that adds up to 400. And you might add down that way, right, to get the totals. It's asking what is 2 additional variables you would like to know in this study. Oh, it says draw a probability tree illustrating that. So it specifically says a probability tree where you get the chance. You could say there's Democrats and Republicans, and then there's interest in the book or not, so you could do that one. Or you could start splitting it. Some people are interested and some people are not. And they're either Republican or Democrat or Republican or Democrat. So either way, like that, there's 2 ways to split it. Then this chiropractor is expected of overcharging companies, the insurance to prove his innocence. The chiropractor submits some records as an example of billing. And then companies have these records examined. What type of study is this? What are the units? What are at least 2 variables that might be recorded about this chiropractor's bills? It's not a survey, right? It's not an experiment. I call it an observational study because it's just the data that are coming from this thing. It's not any type of randomization used at all, right? If the auditor doesn't detect any overcharging in the analysis, is the chiropractor innocent? Not necessarily, right? I mean, if it's not under your control as the researcher, there could have been manipulation. These could have been the ones where there was nothing done, but the other ones could have had fraud or something. And how would you do a study better to investigate whether somebody is being honest with their numbers? Yeah.
Check the insurance companies maybe.
If you go back to the insurance companies, maybe see if they have any problems. So you can do kind of a deeper dive into some of those. But which records do you want to look at? It might be kind of time consuming to look at all the records. So if you have, yes.
Have multiple auditors.
You could have multiple auditors, they might be able to pick up different things, right? But if you had a list over, say, a month period of all the bills, and you randomly picked 25 bills, and say, we're gonna examine those. And you examine 25, and they had no serious problems with those, then you might think it's a good chance that things are really on the up and up. There's not too much fraud going on. It doesn't prove that there's not any fraud anywhere, but if you sample enough randomly and then determine for those. Right. So yeah, if you had a list and could pick them, then you could do more. So then it asks, this one's about drug concentration. I think it's smaller, you can see more. The tablet are measured for 14 randomly selected tablets. Suppose there's a 98% chance of meeting desired levels of concentration. And what's the probability that 12 tablets meet a concentration standard? What type of problem does that seem like? Any suggestions? Yes.
That be a binomial one?
Yeah, this is a binomial, exactly. So 14 randomly selected tablets, that fits your in there. 98% chance, the probability. And the probability that 12 tablets meet the standard, right? The probability that X equals 12. So 14 choose 12, 0.98 to 12. 2% is left over, and there's 2 more of those. What's 14 choose 12? What's a faster way to do that?
Just 14 choose 2.
Yeah, same as 14 choose 2.
It's 14 choose 2, or no, 1 minus 14 choose 2, or would it just?
It's just 14 choose 2. Okay. So this is another way of choosing 12 tablets to be good out of 14. That leaves 2 that miss the mark. So it's quicker to do 14 choose 2. Right, so this is 14 times 13 over 2 times 1. So 7 times 13, so that's 91. Get that number there. Your calculators might very well have something that computes combinations. It might even have something that does binomial. But do write down the formulas, because if you get the wrong number and don't have anything else written there, I have no way of giving you partial credit. And yes.
How much should we study things like the sensitivity, selectivity, and like the PD plus, PD minus thing?
So I don't think I'll give a question that just out flat says calculate that based on a table. Right? But it'd be more, comparing test procedures, which is better, higher or lower sensitivity, higher or lower specificity. Right? So it would be more in comparison. So we did a little bit, more on that so you get some experience with it. But, as these are, it's more computing from a table, kind of just computing probabilities, data that probabilities, turning a 2x2 table into a tree, perhaps. Yeah. So it's, I would not put that as an emphasis to memorize the formulas and how to do that, but rather memorize the other formulas that we talked about. Right. This one, a machine makes tablets. They're too small at a rate of 1.3 per 10,000. What's probably the fewer than 3. So it has a rate there, so it's Poisson. And fewer than 3 is 0, 1, 2. Right, 2 or less. So calculating those two problems. Yeah.
So to clarify, like when the question asks exactly a certain number,
Mhm.
is that still Poisson or is it something else?
It can be Poisson, right? So if it asks, what's the probability of 3 tablets? Right, then you can just go. So if the rate is 1.3, and the probability that 3 tablets in a group of 10,000, right? The Poisson rate is the rate cubed. G is negative 1.3 over 3 factorial. And so that would just be the probability, so just for a single number. And it's possible that I would ask for a single number and then less than something. So we would do a single number, and then you have to add together 2 or 3. All right, so exams on Wednesday. Office hours tomorrow. Email for questions. I'll go to my office and post the homework 4 solutions, so you can check those out. Bye. You.
Have a good one.
Have a good one.